Assalamualaikum and very good morning. First, thanks to a MACE, Malaysia Automation Control Engineer Societies, give opportunity to me to share with all of you what my group, what current research activity in my group, specific on flexible and wearable devices. So my sharing session today, the topic is emerging bendable electronics and how we do the integration with the microfluidic system platform for the healthcare and biomedical applications. So this mind group, we work collaboration with a group by Professor Dr. Marati Jaafar from School of Materials and Mineral Resources Engineering. So this is my outline for my session today. So I will introduce what are my group research field, and then that we continue how our group motivations, why we want to explore on the flexible devices for bio and the physical sensors applications. Then we continue one of the example devices was fabricated in my group in our centers as a strain sensors, and some example how we are tested printing using the inkjet based printer to printer on various substrates such as like PVA, TPU, and also and the last I summarize my talk and also the future works. Our group, we are focused on the sensor development and also the in and a circuit design. Sensor development, so we are focused on the two technologies. The first, we focus how we can fabricate the sensors using the silicon micro machinings, and we explore also how to using the printable electronics using the inkjet-based printing. Then we do the integration with the circuit using a CMOS process technology to develop a complete devices such as like the LED on chip or the LED on skin system. So, as a generally our group, we are focused on the sensors and also the CMOS based circuit. But for the topic today, I will focus on how we apply, how we explore the printable electronics to develop the sensors. So what our motivations? What our motivations on using the Distosable electronics? So if we go some statistic on the aging populations, so like in Japan, they are based on the WHO. If our society aging rate at 6-7%, we consider as a aging society. So if the society aging rate more than 14% is considered as a age societies. But if society aging rate exceed 21% is considered as super age societies. Based on WHO, the definition of the aging where the more than 65 years old, right? So if we go some statistic where the Japan by 2017, where the exceed 21% is to go to 27.3%, and by 2025 where the aging rate is go to 30%, so it's go to the super aging societies. And if we go to the worldwide, so by 2020, 13 countries we go to the super age societies, and by 2030, 34 countries we go to the super age societies. So when we talk about the aging people, so they need caretaker, that means the caretaker to assist them in terms of the health monitoring and in terms of their movement. So that if we have a devices, so I mean if we have a good devices, some that can be attached on clothes and can be attached on the body. That can be the real-time monitoring. That's why it go to the Distosable electronics. By using the Distosable electronics, is can able to attach on the skin without disturb their convenience. I mean, there can be a comfort on the skin, and also if we can also can be attached on any the body tissue that towards to the new devices such as we call a smart bandage and also for the wound monitoring. So I mean we need some innovation devices that can help them to help longevity societies. And then we talk about if we go to issue of the diabetic. So the global estimate where the Malaysia be the among of the top 10 countries by 2030 is we don't have a diabetics, right? So when we talk about diabetes, have diabetic patient, they have some the food ulcers. The food ulcers, so that can have a chronic wound. So right now, how they do the monitoring, we have a bandage and then we do the dressing. But we cannot monitor the precision how the wound conditions, right? So I mean the doctors have to open the bandage and then they can see how the wound condition. But if we have the devices, if we have the system, so that can be attached on the bandage and then can be able to monitor the wound without open the bandage. So that can be some we call as the closed loop system. So that can one of the motivation why we need the flexible, why we need the wearable devices. As example, can be attached on the bandage that can be monitor the objectively how the wound condition without open the bandage, and also the doctor also can be object the objectively decide. So when the patient should be change the bandage and when the patient will come to the hospital to do the wound dressings. So that also can help, that mean to reduce the costing, that mean the burden cost to the patients. So in terms of the wound, based on one studies, if we can monitor the wound pH, that means how the pH condition, the pH value at the wound conditions. So I mean if the pH are more than 7.15, mean it easier to have bacteria, so that can we create the infection. So I mean if the bandage can know what the exactly pH value at the wound condition, so that the doctor can be decided what is a suitable the antibiotic, what the suitable amount of the antibiotic to kill the bacteria. So from one study, if we can monitor the pH and we can monitor the oxygen levels and at the and of the skin temperature at the wound condition can help to faster the healing rate. So that can be one of, so to have that system, we need some technology we call as wearable or the flexible devices, so that can be attached on the wound without disturb the convenience to the patients. So with a two motivations, so by improve the aging societies and then to improve the aging society monitoring and improve a wound monitoring, that one of the motivation in our group why we go explore on the the stretchable and flexible devices. So if we to understand how to develop the bendable, the flexible devices, based on one this journal was published by Professor Michael Dideki, we have three technologies to develop the flexible electronics. The first we call as the deterministic geometrical. The second technique we call as the random composites. And the third technology we call as a intrinsic. So what is the deterministic geometrical? So these technologies, how we need to have a carrier substrate, such as like a silicon, so that on top of the silicon, we do the thin film deposition. Then we have go through the lithography process, and then uh, to do the patterning, like the zigzag patterning or any like a spring uh, patterning, that to improve the stretchability of the device. But after we done the patterning, we transfer the pattern on the other subsets, as like the polyamide, and then towards to the flexible and stretchable. So by using that technology, we need the complexity of the equipment to do the patterning, to do the lithography process. And then the second technology they call as a random composite. So random composite. So there is some how the formulation, for example, how we make it the insulator to be the conductive. So the insulators we the less conductivities. So how to make it the insulator to be conductive, we have so some of we call as the random composite, we mix with the nanoparticles, such as like the conductive nanoparticles, such as like silver nanoparticles, and then to make it the insulated, I mean the polymer can be a conductive, because the material can be stretchable is a polymer. Such as this is some we call as a TPU. The TPU is a polymer substrate. So it can be stretchable, but it's not conductive. That's why we need mix with the nanoparticles to create, to make it the insulators, the polymer to be the conductive polymer. That we call as a random composite technique. That is second technique. The third technique we call as the intrinsically stretchable. Means so we have some PDMS. So on top of PDM, so we have the micro channels, and then we using the ionic liquid in a channels, then to make it the stretchable. So when the fluid is movement, so that can tune the stretchabilities. That means they can correlate to how, based on movement, how they're stretchable. So this is a three technique that available to develop the bendable electronics. So we have the deterministic geometrical, mean on top of the thin film, such as like we have the silicon wafers. So we fabricate, we deposit thin film, and then we design the patterning, the geometrical patterning. And the second, we have the polymers, and then we mix with the particles to make it from the insulator to be a conductive. The third we call as an intrinsically stretchable, mean we using a fluid, the ionic fluid in the channels to based on their movement, so that we can have the stretchabilities. So these are three techniques, but in our group, so we try to make it what is more a simple technique to make it the bendable, to develop, so that we use a second technique we call as a random composite techniques. So that we need to do the formulation, the ink formulations to make it more conductive. That's why in that research we do the collaboration with the material expert, Prof. Manaf, that means to do the ink formulation. And if you based on my previous slide, so if you want to apply on the wound, that means on skin for the wound monitoring, that means the ink, the material must be the biocompatible materials. So this is some of the example. The first technique they call as the deterministic geometrical technique. So this is a paper was published by Jonathan et al. In a Nature Communications. So this is a few design that was designed by that group. So we call as the Von Cost curve or the piano curve, Hilbert curve, Murray curve, reset fractal, and the quick cross. So we need, like I explained before, so we need the carrier like wafers to do, that means to design the pattern on that on that carrier substrate, or we use the silicon wafers, and then we have go to the lithography, and then to do the etching to create the pattern. Some we use like the iron, a gold, or a copper. For example, like we deposit the copper, and then we do those type of the structures, the geometrical structures, and then we transfer the pattern on the permanent substrate. So that is some of the example, like the Japanese uh, uh, origami, right? So that means they can, by having the geometrical, so that can be improved in terms of the traceabilities. So when but in our group we try to focus what is the simple technique, more a simplified technique to do the fabrication. I mean to develop the bendable electronic devices. So this is some a few the other groups, the wearable devices, some from the Prof. Somaya group from a Tokyo University. So a lot of people they done some the epidermis electronics that was published at the science the science in the 2011, and a few this for the hydration sensors to do the hydrate the skin hydrations, and also the blood oxygenation on, and also some they go study in term of the sweat analysis, and then they attest a sweat. So some they using we call as a ion tophoresis technique. So they have the anode and cathode, so that can be the potential we activate the sweat from the glands, from a glands, and then go to the skin surface, and then do the detections, right? So this is a so if we can have a those type of wearable. So for example, like if we go to the ICU, so a lot of a cable connected to the instrument to monitor the heartbeat, to monitor the heart rate, and the temperatures, the body temperatures. But if we can have the attach the patch, so right now we talk about the Internet of Things. The Internet of Things, the most important how the these technology, I mean the sensors technologies. So if the sensors can capture the accurate data, so all those those data we send the remotely this wirelessly can send to the cloud. So that can be avoid the messy wire and cable in the ICU. So if we can have the ultra thin film substrate, and then we can have the that we develop the sensors. So of course we can easily monitor the human the physiological signals. That can be help how to assess the health assessment and disease diagnosis. So like I explained before, for example, like the case for the wound monitoring. So if we can monitor what is the pH levels, so the pH level we consider how the bacteria grow in the wound condition. So if the pH is more alkali, there's more than a 7, so it means the more bacteria grow. So that means now your wound have the infections. So by knowing the pH, we can correlate what is the correlate how the number of dose. That means the antibiotic can be dispensed. What type of the antibiotic based on the pathogens, right? So this is some new the that can be by having that technology we can have a new assessment, a new health assessment to help the doctors and the medical doctors to the, their decision, right? So, for example, in our case, we also have developed the strength as sensors. But if we have a good the sensitive strength sensors, so that we easily to do the precise monitoring the human body activities such as how they join the fingers, the hands, arm, and leg. So that can be can help. That mean to assist their movement. That mean their health monitoring. So that's why in our group, so based on that motivations by collaboration with the Prof. RR Dr. Matis, so we continue to do the ink formulations. So the ink formulation was done by group from the School of Materials that but must have a biocompatible ink. That we do the sensor design, and then based on our sensors specifications, so the group we do the do the ink optimizations, so that we using the inkjet printers, we using the inkjet printers to develop the sensors. So in term is a really challenge to develop the ink, right? The first, the a few specific for the ink. The first, how good your the ink will determine how good your printing technologies. I mean, how good your printing the resolutions. The resolution mean what is the minimum piece that we can print it, and also the accuracies. So the accuracy is a we want to print that line on that position, but after the end product, we can see they have the misalignment. I mean, how far? I mean, the distance for alignment. And of course, the second, we must to ensure must be uniformity over a large area. I mean, if we do the printing, so that mean with the large scale, they have the same thickness, the same uniformity. And the third in the fourth is the compatibility in with the printing components. So mean so that is how we decide how good your ink viscosity. For example, if your ink viscosity is the highest or the low viscosity, also they will determine what is the suitable the cure temperatures to make it your ink a fast cure. So that can be avoid the ink can be the line can be the overlap is others. That is called the and then next the portability of target substrate. I mean, if you want to fabricate on the TPU, so how your ink formulation? The TPU is one type of the polymer substrate. We call it Teflon polyurethane. So if you want to fabricate to print it on like the that's the polyamide, so they also what is the suitable ink. So it means they have also a study how the portability ink and then cover in and with the target substrate. And of course, the last, the throughput, how fast your ink can do a printing. So that we do the calculation based on the printed length per unit time or the printed area per unit time. This a few, I mean there's spec that you have to consider when you do the ink development. That's why, like for example, like the Canon only applicable the ink because the ink already done from it need to be considered some study by the Kenjiro Fukuda and Takao Someya. They study a few type of the printing technique. Of course, some they also have the print screen, the the screen print technique. The screen print technique, if you compare to the inkjet, the screen print they can waste the ink, but the inkjet, so we can minimize the ink usage. That also we can do the small piece, and then it's a good in terms of the more can be or more precise control of the thickness. It's also a compare to the speed. For example, like the inkjet can be the 1 meter per minute, 1 to 500 meter per minute the speed. So this is some so that's why in our group we do how we can do the ink formulations, and then and for the inkjet based printing to do the sensors. Okay, so when we talk about the stressable, so the stressable mean the ink also not, for example, now your substrate is a stressable, but if your ink is not stressable, so when you stress, the ink will be appear off. That's why your ink also must have the stressability to follow the substrate when the substrate is stretched, right? So that's why one of the examples, so that we they using the PDMS. The PDMS is a polydimethylcellulose. This is a polymers, and of course there is a insulators. Less the conductivity is less is compared to the no. That's why how to improve the ink the conductivity, we need to add with the particles, nanoparticles. One of the example here is the silver nanoparticle. This is one of our ink formulation. So we do the combination between the PDMS and then that the PDMS, and then we add with the silver particles. So we add with uh, the silver nanoparticles, so that can works to this in the stressable conductive ink. So this is some so from here, so we do some studies, I mean to mix, so because the mixing, the ratio of mixing will determine how good your conductivity. So if you increase more silver nanoparticles, of course they will increase more conductivity, but they will increase the costing of your ink. But if we do the less conductivity, the less ratio of silver nanoparticles, of course they will reduce the costing of the ink, but of course they will decrease the ink conductivities. So this is the trade-off. We have the trade-off between what is the suitable silver nanoparticles ratios with the polymer such as in our case with the PDFS, and then to improve the ink conduct activities. Of course, we have to have uh, the baseline with a copper, that means 10 power 6. That's a good the conductivity, that how implement in our PCB fabrications. So this is some our studies. So some of our papers was published in our student Han Min So. So that is one of our papers. So we published on the Journal of Material Science. So this is one of the examples our study on the ink formulations, and we tested we apply as a strain sensors for a strain sensor. So here's the AG that the silver, so that our PDMS, the polydimethylsilicone. So that's the PDMS. So this is a PDMS. So and then we mix with silver nanoparticles. The 2025 we consider the weight of the particles, the percentage of the particles. For example, here that means is so the so PDMS with the 0.20% of the particles, all 0.25. So this is the ratio, the mix ratio of the silver nanoparticles and the PDMS to set, that means to improve the conductivities. So from that study, so we have a few, so that the of course we can see here. So we have the two type, the PDMS composite, and then the with the the silver with PDMS composite, and then silver with the PDMS. So that we can, of course, if we improve the silver nanoparticles percentage, of course, they will also increase the conductivity of the ink, right? So we try a few formulations, so that we come to where the 25 and 20. So the 25, so we can do a testing on the strain sensors. So we on the fingers movement, and then we evaluate, we do the analysis, what is the maximum strain. Okay, so that is one of examples, uh, the 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 strain sensors fabrications in our group. So this is one of the the output from one of our students, Han Min So. So this is one of our first we done the fabrications to for in using the PDMS, and then we mix with silver particles. So in our group, so by that the ink formulation was done by the Prof Marathi group. So they do a lot of the formulations. So the AG 0.20 is a represent the percentage, the weight percentage of silver nanoparticles. So of course, based on that data, so if we improve the ratio, the numbers, the percentage of silver nanoparticles, then also we increase the conductivity, the conductivity of the ink. So in that, so we focus on by mix with the PDMS. So this the PDMS and also the PDMS composite, and then we do the evaluations for the strain sensors evaluation. So the strain sensors evaluation, we using a concept of the resistance. So the changing of the so when stress, so the L will be a changing, so that can be the changing of the resistance. So from that evaluation, so we do some the evaluation of the strain sensors in terms of the gas factors, and then what is the maximum stressabilities. So how we consider the maximum stressability? So mean after 70%. So if we turn back, that mean if we back to the initial, but the hysteresis still can be under control. So this is some the gas factors for the silver PDMS. So the value about the range between the 12 to the 25, and the sensibility can go to the 70%. And also for the PDMS composite, we add with the silver nanoparticles is it go to the gas factor is the 8.46 to the 10.4, and the strength also can go to the 70%. So that is some of the example. That is one the printing that we have in our lab. So that we have the inkjet printing. So we have the cartridge. How we do the research? So we bought the empty cartridge, so that we fill in the ink formulations from our collaborators. So that we do that we print the sensors pattern. So for that is some of the example, the TPU, the the TPU substrate. So the TPU substrate. So we do a printing. So some of the examples. So we, of course, when we do the printing, so the ink was formulated by the group materials. They must be suitable with our pure temperature, where the pure temperature is about 120 degrees. So this one of the 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 ink specification that must be developed by our collaborators. So, and then the second, the ink must be have a biocompatible ink. So the currently in our group, we also focus on the first accessible conductive ink, how we mix the PDMS with the silver nanoparticles, and also we also focus on the graphene-based ink, the carbon-based ink. So such as like the CNT, and also the reduced graphene oxide ink, so that can be used to develop our sensors for a wound monitoring, for a pH sensors, and also for the temperature sensors. So this is some a few we do the characterization. So this is the ink that we develop uh, developed in our group. So we do a testing, how that mean we put on our back hand to do the motion testing. Then we can see how their sensitivities, I mean how they're sensitive for the back hand motions. And the second, then how sensitive, I mean we do the wrist stretching test, and also the finger detection test. So in our setup, so we put a so we set up on the glove, on top of the glove. So we attach our fabricated strain sensors, and then we do the analysis. So that data we also publish at the same journal, I mean the Journal of Material Sciences. So, and other than PDMS, the currently we also working on the printed. I mean how we can print it. So that is this is one of the example substrate. That is a TPU, the Teflon polyurethane substrate. That's a TPU substrate. So and with this slide, that is the PVA substrate, the polyvinyl alcohol substrate. So this substrate is a water soluble substrate. So what we are going to develop, so mean after we done a printed, after we have printed the pattern on the PVA substrate, and then we attach on the body, and then we use the evaporation, that means the heat, to remove the area where don't have the pattern. So then they can be removed, that only a pattern can be attached on the skin. So it can be like the conductive tattoo, right? So that is, and then we also done a tested, the just done a tested on the other subset, we that the gelatin subset, that's a gelatin. So that maybe is some application for the humidity sensors. And this is some of the examples we using the bandage. So from the Medic PU transparent, and then we also tried. We also done a tested. We also printed using the inkjet printing on the bandage. So that is some of the various subset that we done, and also the common also do the printed on the polymer subset. But the polymer is only the bendable, but it cannot stretchable. So so this is a few subset that we focus in our group. So we by control the ink formulation in terms of the wettability, in terms of the viscosities, in terms of the mix ratios, and then the particles, and also the polymers. And then we tested a few the substrate that can be applicable for the bio and the for bio sensors. And the others, we because we also done a few testing. That means we do how we can design the circuit, the flexible, the bend, the the flexible circuit. So this is one of the examples. So if a normal PCB, so when we design, so that can be we do a sub edge. But when you apply in the flexible, when you stress, so that can be the possibility at the sub edge will be cracked. That's why if you design a circuit, when you design the circuit for the flexible, for the printable circuit, we need to study also how the curving, the curving, the curving to increase the robustness of the flexible devices. So this is one of our tested. This is a normal circuit. So this is some that we do a printing the flexible uh, circuit, so that we can do a printing to do some tested on the printable. I mean on the how good that printing the circuit. That means how good the ink can be applied as a circuit trace. So this is one of the examples. So the temperature we check the temperature sensors, this just to prove that in is a sufficient to drive the current. We need to turn on the MCU, and then to go to control the temperature reading. So this is some current that we use the inject printings, and then that on the TPU. So that on the PVA subset. So there are few some uh, advancements in the flexible electronics. So, and in terms of the fluidic base, so because the other technique, so we call as the stressable electronic. One of the concept we also apply for the fluidic base in to improve the to develop the tunable inductance. So one of the when we develop the inductance, the one of the the control is the number of turn, right? So it means the number of turn. So we determine how your inductance values, right? So now in our group, we also focus how we can replace the core to be a fluid. So that means by control the fluid movement, so that we can changing the number of turn, so that can be tune the inductance. So this is some the overall concept of so this is the coil. So the coil structures. So that is the channels. So that channel will flow in the fluid. So the fluid will be controlled by the external micro pump, and then to control the flow rate. So by control the flow rate, so that we can control the number of turn. So that can be changing. That can be changing the number of that means can change the inductance value. So this is some of the design. So how we the integrations between the tunable inductors and also the readout the CMOS circuitries. So this is some uh, simulations. So we have so this we using uh, ferrofluidic, so that we flow in the in channels, so that can be the changes of the inductance values. So this is some hours studies. So for example, this is some the EMG 901, EMG 905 is a type of the ferrofluidic. That's we purchased from the Ferrotex corporation. So the each ferrofluidic they have a different the dielectric constants. So with if we see at the 100 megahertz, at the 100 megahertz, so we can hear. So at the blue color is referred to the type of uh, the 901, the EMG, the type of fluidic in at the 901, where the at the 100 hertz, where we can see the quality factors is about 53.7, and about the tuning ratios, the tuning ratio at the 100 where is about the 83.5%. So that how we using the ferrofluidic, we using the ferrofluidic that we insert in the micro channels, that we have a fabricated coil, so that can improve the tuning. I mean the tunable inductor. The good is by using the fluidic base, so we can have a continuous tuning, and we can control the precise uh, tuning inductors. So this is some our target. So at the current, so we have a strain sensors. Now we also developing the temperature sensors. We using the RTD, the resistant temperature difference, the RTD sensing mechanisms. And also we develop the pH sensors that using the RGO, the reduced graphene oxide, and also with the heater. So that is one of the our current, I mean, to for the wound monitoring. That means to detect the physiochemical signals, the pH, the skin temperatures, and also the pH. So that we integrate with the commercial MCU, so that can be the wirelessly transmit the data to the mobile phone using the Bluetooth, the B. Some we can use the Bluetooth, the B, at least the Bluetooth low energy uh, topology. So this some of the that we call as the system on film. So that means on film that we consider as on one substrate, on the flexible substrate, but we have the multiple sensors, we have the temperatures, so we have the pH sensors, and also we we have the oxygenation sensors. Right now in my group, we prove in terms of the strain sensors development using the ink formulations, and also now we also have the develop the CNT and also the graphene based ink towards to the temperature sensors, and also for the as a sensing membrane, also for the pH sensor development. So this is some memory for today. So we successfully do the ink formulation by mixing between the PDMS as a polymer and the silver nano particles. And also we are in a progress to develop the biocompatible carbon-based ink, so that can be using for pH sensors. The pH sensors we are using the electrochemical sensings, the EC-based sensing technique, and then for the temperature, we are using the RTD sensing techniques. So for the strain sensor, right now we done a tested with silver, the missing rate, so the 0.25%. So we have about 12.76 to the 25.74, with accessibility about 70%. So that and also we prove some the ink sufficient to drive the circuit, I mean to drive the current. So that can be potentially, that may have a potential to using as a circuit trace. So in next step in the future works right now in my group, we are still in a process the optimization the graphene based ink, that how we are going to use as a sensing membrane for the our working electrode for a pH sensors, and for the heaters, and also for the temperature sensors toward to system on film. Thank you.